Today we'll just be reviewing the calculus type material for today's exam. So what do we have? I know at least one person has asked me, and it comes down to really only two things. We have calculating the work or potential energy from a force, or calculating the force from a potential energy. So that means it's not going to take me all that long to review the calculus stuff. There should have been also center of mass, but I had that in my lecture combined with other stuff, and we didn't get through enough of that for me to put a center of mass question on the test. So let's go straight to looking at how we would do a calculation. And there is one thing that is new in today's lecture, and that's this check. Suppose we have a force described as shown here. Is this a conservative force? Now, what's the definition that we know for conservative forces? Okay, they give us back the energy. We can store energy in them, but they give it back. They don't keep it. Well, there is a mathematical equation we can use to test to see if a function is conservative. I actually used this at the end of a lecture a few days ago. Well, a few days ago, I guess that would be a week ago now, wouldn't it? And that is that the curl of the force has to be 0. I think that's what curl is, right, Del Cross? Somebody? So he's taken math within the last 25 years. Okay, so let's just check this to see if this is a conservative force. So mathematically, to do a cross product, it's multiplying the perpendicular parts, and we do it in the determinant form. So I put x hat, y hat, z hat. Always start with that. So the first row is your directions. The second row is the first item in the cross product. As you may have figured out when we talked about right-hand rule and left-hand rule, I didn't explicitly mention this because I forgot. If you replace the positions, you get the opposite direction, right? Torque is R cross F. It is not F cross R. That would be the opposite direction. So the order is important. So the first item in the cross product is the next row. And so that's going to be del, our gradient vector operator, which is in the x direction, d dx, in the y direction, d dy, and in the z direction, d dz. And then finally, I have the second part of the cross product, the force vector. So using the function up above, and I'm going to ask you now, what do I have in the first column for my force function? Ax squared, because it's the x component of it. What about the y component then? Negative b over y. And the z component? And so then I have to do the calculation of this determinant. So now, once again, with the determinants, it's important that when you do it, you have one row, take the first row, and then multiply it by the determinant of its co-matrix, always going top to bottom as you do your determinant. You know, when I was it was high school when we learned to do determinants, I think. And my teacher taught us things like, you know, this and then this. That isn't right. It has to be like that. Otherwise, we would have something times the derivative instead of the derivative acting on something. So that order is actually an important piece that actually, my high school teacher was pretty on top of things. She probably did know this. I didn't know, of course, when I was in high school. So I take my x hat times the derivative of its co-matrix, which is going to be derivative with respect to y of cy. What's that? C. And then I go the other direction, of course, minus for the one that is going from top right down to bottom left. ddz of minus b what? Y. What's that derivative? 0. Now, why is that 0? This is the beauty of that. Okay, that was a rhetorical question. Why is it 0? It's the beauty of the partial derivative. We're just treating anything that's not z as a constant when we do the partial derivative. I think you can see the answer already. In the x direction, my value is not going to be 0. Technically, I don't even need to go on because that's enough to say that this is not equal to 0, hence it's not conservative. But I will continue on just so we can have the practice. I'm doing it this way just so people have more practice with the cross products. So for the y, I have my y hat, and I need to put a minus sign with it. Why is that a minus sign? Okay, I heard because, and I didn't hear the rest of it.
That's how you learn. That's how we do
That's how we do them. You have that Levi-Civita symbol, the thing to keep track of the signs. And basically the rule is positive, negative, positive. It just alternates signs with each term. So minus y hat times derivative of its co-matrix would be derivative with respect to x of cy. 0. Minus the derivative with respect to z of ax squared. 0. And then my final term, plus z hat, back to plus because we're alternating signs. And then that's going to be d dx of minus by, d dy of ax squared. Now we've done it completely. So that was not a conservative function, right? That force, was not a conservative force if that's the given force. So this is actually something new for today, a way to check to see if a force is conservative or not by its mathematical form. Question, Jonathan?
Couldn't you just take a look at the equation and look at each one and say, okay, is there any, how do I say this? Like,
I think I can say what you're saying.
Right.
Can't I just look at that and say, is the x component only dependent on x? Is the y component only dependent on y? Is the z component only dependent on z? If the answers to all of those are yes, then it's going to be conservative. But if the answers are no, there could be, depending on what the numbers are, situations where it's still conservative.
Because it cancels out.
Yeah, because I could have had, I use a constant c here, but I could have had a number here and I could have had another number somewhere else that would have made it so it would have had c minus z effectively. Usually not going to be the case, but it's possible to make one that does that. Question over here.
As far as explaining the concept behind a problem like this, if it showed up, would it work to describe, that a conservative force should have a curl equal to 0?
Yeah, if I asked you, is this a conservative force? You would say, it's conservative, the curl is 0, and then do that. Okay. Next, oh, by the way, remember going back here, I got most of the way through showing this relationship, but I didn't quite finish it. Well, I said, and the other terms has to come out to 0. I made a mistake when I said that. I went back to my office and finished out the work. And of course, I realized at the end, the other terms aren't 0. In fact, when I did it, I had, the first term, I said, these are the ones that are the force components. But I didn't notice that the signs were wrong. They have the wrong signs. But if you do the next two terms using the restriction that for conservative force, the curl has to be 0, turns out the other two terms were both negative the force component, giving you the right sign in the end. The other two terms, so you have like plus force x, minus force x, minus force x, which gives you minus force x for the x component. And so I didn't finish my problem right, and I made a statement that was incorrect because I hadn't finished it. I had thought to myself it was going to be simple, goes out to 0, and it wasn't. So just a correction on my work, because I know probably to everybody here, they're like, whatever. But I hate to have wrong information left on the table. Okay, so now we're going to take a corrected form of this function. What did I do? I followed the pattern that Jonathan recognized. I made my x component of force just a function of x, my y component just a function of y, my z component just a function of z. So it's going to be conservative now. And then I said, what is the potential energy function associated with this force? Going to do that first. Then we're going to reverse it and say, okay, now that we have the potential energy function, what's the force associated with this? So we can do it both ways. So we start, what's the potential energy function associated with this force? Obviously, in the equation sheet, you should have this. I haven't looked at the equation sheet. I actually forgot about that. I was going to edit it last night, but I was home and I don't have the software necessary to edit it at home, so I couldn't. So our equation is that the work, which is equal to minus the change in potential energy, that's the definition of potential energy is by the change, is the integral force dot distance. And for three-dimensional situations, the force vector, we write x component in the x direction, y component in the y direction, z component in the z direction. And dr we write as dx in the x direction, dy plus dy in the y direction, plus dz in the z direction. So to do this work, I'm going to do that. I'm going to say change in potential energy equals minus the integral
So you're gonna put that equation on the equation sheet?
well, it will be this here on the equation sheet, right? You will need to be able to expand what force vector is and what dr vector is. But I will put that equation on the equation sheet. Is it not there now? Do you have it printed out? Because, like I said, I was going to edit it last night and I couldn't.
Oh, I think it is.
It is. Okay, good. Feel a little better. So now I'm going to put in my integral, and I actually have three integrals, right? Because I have dx, dy, and dz, but I'm going to just have one integral sign input. So I have that dotted with, I didn't give myself enough space. Okay, got myself enough space now. Now, everyone here is a pretty astute mathematician. When you do a dot product, which parts are you combining? Parallel parts. So what's parallel to x hat? Obviously x hat. So when I do this, it becomes three separate integrals. Correct? Now, I did not put any limits on here. I'm going to put limits for a reason that will actually become important. Usually we don't put limits here. We say just plus constant. But here I'm going to put my limit. So I'm just going to go from x0 to x final, y0 to y final, z0 to z final. And then I just evaluate each integral. What's the integral of ax squared dx? Okay, ax cubed over 3. Notice I just realized that I forgot to bring my minus sign through, so I put the parenthesis there so the minus sign goes through now. So I'm going to have minus bracket ax cubed over 3 going from x0 to x final. What about b over y? Okay, so that's going to be minus B natural log of Y, going from Y initial to Y final. And then finally, plus, what's this one? Okay, so now I just have to apply my limits. And at this point, I'm going to drop the F's off the finals, when I put in my limits. So I'm going to have equals minus A over 3 times x cubed minus x initial cubed plus, because minus times minus, B natural log of y over y initial minus C z squared over 2. Whoops, I was going to put in my limits, wasn't I? C over 2 times z squared minus z initial squared. The reason I put in my limits is because mathematically you can't do the natural log of y, because y has units. You can't take the natural log of something with units. So that's why I actually put my limits in here, so I could have something that is mathematically reasonable. So here is my change in potential energy. Potential energy is defined by the change. It's not defined for any location. It's defined as the change between location 1 and location 2. So you can always have an offset to your potential energy function. So we traditionally would say something like, let my reference potential energy equal, and obviously you can just read the things that have the zeros in them, ax0 cubed over 3, and then I'll go to the last one, plus cz0 squared over 2, and then I have that middle one. Once again, technically, I can't get that y0 out by itself. And so we end up with a funny situation. And also, of course, if you have y0 equals 0, then you have the natural log of something that's either plus or minus infinity when you do your work. So I'm going to let that equal 0 and not worry about the y portion. So I have kind of a hybrid here for my potential energy function, so I can have the units right. So that will let me say potential energy as a function of x, y, and z is equal to that. So there's our process of going from a force function to the potential energy. Confident you can do that? No? Okay, let's review the steps then. The steps were step 1, recognizing your equation there, that potential energy is defined as minus the work. And then works, and it's only defined for conservative force. So we had to start with, hey, it's conservative force. For conservative force, potential energy defined as minus the work. And so then I used the work integral. I expanded the work integral. That is, I put in my force as a vector function, and I put in my dr as a vector dr. Then I applied the dot product, which made it much simpler. And then I did the integral. And that last step about letting potential energy reference, that's an arbitrary decision. It's absolutely arbitrary. You could have said, I'm going to put my reference potential energy is 0 at x equals 3 and y equals 5 and z equals 7. You could have done that. It just would have made the function look a little longer. And so I did the arbitrary to make it the shortest function I could. Felt a little better? Brady.
Just kind of like that question. So by setting the potential energy 0 equal to 0 at those points, that'd be relative. So we're looking at a two-dimensional coordinate system. So that's wherever you want to pick on the graph is the zero potential energy state.
Yes.
Okay.
Basically, if you make a graph of potential energy versus position, it is arbitrary where you put the 0 points. You have a graph that's going to look like this for your function, and you can arbitrarily set any level to be the 0. But you set it and then you stick with it. Okay, for our final trick of what I have set out today, let's reverse that. So we have my potential energy is minus a over 3x squared. Hey, look. Okay, pen stopped working. So I am going to try my new trick of let's kill the app. That was not kill the app. Close window and try to open it again. And that was a good sign, right? So that was my function. And now having that function for potential energy, I want to find the force. Well, if this problem were to come up on the test, you'd say the force depends on the gradient of the potential energy. That's great here. Del of the potential energy with that minus sign. If we want to put this into things that will make it stick in our brain, which kind of I want you to do, I want you to remember this. The natural thing to happen is for things to go to lower potential energy. The force is essentially how strongly you're pushing toward lower potential energy. And so if you make a graph of a potential energy function, that is, let's say I had something simple like, just as an example, changing pages here. Let's say I had potential energy was equal to 1/2 kx squared. That's the function for a spring. If I graph this, so I'm going to have position on this axis, and on the vertical axis, I will have the potential energy. Okay, let's be consistent. If I graph that function, what in the world did I just, I made it not full screen. If I graph this function, it's going to look like a parabola, so it's going to be going like this. Okay. Imagine that that's a perfectly symmetric parabola, if you will. Try to make it a little better. Okay, so my parabola looks like that. If you just think about something simple like, let's say I put a marble on that, and that was a physical ramp. The marble, if it's on the right side, it's going to have a large amount of force pulling it in the direction that it could roll. You get down closer, and the amount of force is getting less because it's not as steep. So the force that's going to be actually pulling it is just going to be proportional to the slope. And of course, what is the slope mathematically? The derivative. And so this gradient is just allowing us to do it in 3 dimensions. So you can see the relationship. Anytime you see a graph of potential energy, you can see what the force is going to be like. Just look at that and say, okay, the slope of this curve is going to tell me what the force is at any location. Because I know the acceleration here, if this was a ball sitting there, would be much bigger than the acceleration there. So we have our equation. Now, something you may or may not be comfortable with, we often use the symbol U for potential energy. Higher level physics uses either U or V depending on the subject for potential energy, and either K or T for kinetic energy depending on the subject. Isn't it good to know that your variables are not consistent? So I'm just going to take the gradient of the potential energy. So I write out the gradient. Do I have the gradient on the equation sheet? It better be there. No? Okay. I will edit it when we get out of class and make sure it's there. Notice we will get a vector out when we do this because we have directions with each derivative. Ran out of space, but there we have it. That's kind of sloppy, but it kind of fit. I guess I can do better. Sure, I can do better. Life is good, not the euro sign. Just going to read. Okay. No vectors on the potential energy, right? It's a scalar. So now I just go through. Equals x hat times, and I take the derivative with respect to x of that function. Well, what do I get when I take the derivative of that function with respect to x? Bring down the 3, lower the power by 1, negative ax squared. And then I'll have plus y hat. Take the derivative of that same function with respect to y. Right? Actually, no. No, that's not right. The y naught doesn't go there, or the y ought, because you have to use the chain rule. And the derivative of the inside would be 1 over y ought, and so the y oughts actually cancel. Which is good, because I was going to say, now I have a problem, because I didn't have it there in my starting equation. Derivative with respect to z. Now this is the gradient of the potential energy. What is my force? According to the equation that's shown right there. It's negative that gradient. So the force is going to be just change the signs on everything here. So I end up with my answer being the force vector is equal to change the sign. So that's going to be positive ax squared in the x direction minus b over y in the y direction plus cz z hat. So now we reversed the problem. We went from the potential energy function to the force. And just for clarity, here's the force we started with. Here's the force we ended with. They're the same.
For a problem like that, you would give us just an equation, not necessarily ax squared, but any equation, and we just go through the process.
Yes, yeah. So the point of the problem would be that you recognize the relationship between potential energy or work and force and can do your calculus.
And our concept for that would be that the derivative force is work and that potential energy is negative work? Or what would be the concept?
Yeah, okay, so if you're finding the potential energy function, then your concept would be that the change in potential energy is defined as, you can't get any more basic than it's defined as, minus the work. And work is integral of force dot distance. That would be the entirety.
And we don't need we need an image, like a figure?
For something like this, I could require a figure, plot a figure of the force to get, so you can see a relationship between that potential energy, or more likely, if I had a potential energy function, I would ask you to draw a figure potential energy function for getting the force, because you saw it's easier to see the relationship for the derivative than it is for the integral, right? The area under.
Can you show that?
Well,
It was just wasn't the
Parabola?
the parabola was an example of showing that, yes. This was showing if I gave you the potential energy is 1/2 kx squared, you plot like this, and then you say the force is equal to one dimensional, so I only have to have minus d dx of 1/2 kx squared in the x direction. But I put my x direction out front for the simple reason that I don't want to look like I'm trying to take a derivative of the x direction. In my situation, the x direction is not going to change, but there are situations where we have changing x directions, so it becomes complicated. So then I would just, you finish it out and you have equals minus kx. Okay, I had actually two questions, but the one that's still up is Gabriel.
So if you gave us a potential energy function, should we just graph it on our calculator and then sketch it, or unless it's
you
simple?
don't need a calculator to graph a function that's a polynomial. Now, if it has a natural log in it like this one did, then it's a little more complicated. And of course, if it's a three-dimensional, I'm not going to ask you to graph it.
Okay.
Is that what your question was?
Yeah, if it's that's not a problem. But something a little bit more.
Yeah, if it's three-dimensional, I'm not going to ask you to graph it. What I'm going to have you do, in a four-dimensional space where the amplitude is the fourth dimension, you can't do that, right? Yeah. Do you have more questions, Brady?
I'm good for now.
Good for now. Okay. Any other questions? Carrie.
What would be the concept for going from potential energy to force?
From going to potential energy, then I would. It's not as simple as it's defined as, but because nature. Well, yeah. What's the short words for it? The long words. I come up with lots of long words. The long words are, natural systems are always trying to go to the lowest potential energy. So the strength with which it's trying to get there, the force, is proportional to the slope, and in fact is given by this equation. That's the long answer. The short answer would just have to point to the equation that it can be shown mathematically that since the potential energy is defined as the integral of, minus the integral of force dot distance, then the force can be found by taking minus the gradient. And that's all you can really go with, right? Because it's a mathematical relationship in the end. Because of that definition, this is true. You're all happy with that answer.
And if you just have two dimensions for doing the curl, can you just have the cross product for the gradient of ddx and ddy?
When you actually do the curl, you need to have all three columns. So
Okay.
you'll just have zeros in the last one, and that's going to make everything that's not z be zero.
Okay.
Z is the only one that's going to have answers that's not zero. Okay, this is all I had prepared because it's the only calculus that we have. So any other questions you have about the test or preparation, go ahead and ask, John.
I was looking at one of the example tests, and it had a problem about moment of inertia.
We haven't covered that yet.
Okay.
Right. Different years I've had different tests. Students complained there weren't enough tests, so I added more tests, which means that our second test isn't covering as far into the textbook. And last year I got behind because I was trying to do flipped learning thing, and so last year's test didn't include chapter 8. So 2 years ago included beyond chapter 8. Last year didn't include chapter 8. Questions?
So for preparing for the calculus portion of the test, at like the past four sessions that we've covered calculus concepts, are those fair game?
It's only going to be what we did today.
Okay. I'm on track.
I trust that was a positive, not sarcastic. Well, no, not for me.
Oh, no, it was
That's
awesome.
great. And I'm like, now
But
is that
it
all
sounds
great?
great.
Like, or was it great? Like, yeah, I know what I can focus on.
So it like reviewed some, but it's like PHYS was just like, there was multiple things that we talked about.
Anything else? All right. If there's nothing else, then let me go edit the equation sheet. I should brought that up because I probably would have gotten to a half hour before exam time and start panicking. Instead, it's an hour and a half before exam